We go. So we are talking about section 3.2. Okay. So section 3.2. This is where we talk a little bit about what is unusual. So we're still dealing with symmetric and unimodal distributions. Okay. So a nice bell curve. All right. And what we want to know is what if I give you some sort of data point, is this data point maybe unusual? Okay. So we want to talk about that in terms of unimodal and symmetric distributions. Okay. So what is unusual? So we kind of use some things to help us out. Those two things are the empirical rule and z-scores. Okay, so this is going to be all about the empirical rule and z-scores. Both of these, which if you've had college mathematics, you should know these. Okay, because we talk about them in college mathematics. So, first thing is the empirical rule. Okay, so the empirical rule says that if the distribution is unimodal and symmetric, then 68% of the data observations will be within one standard deviation. Again, this is that 2/3 that we talked about in 3.1, where if you were between one standard deviation, that was about 2/3 of your data. Right here, this is the actual percentage for it. It's about 68% of the data is between one standard deviation, which again, that is about 2/3 because 2/3 is 66.6 repeating as a percentage. So 68% of the data, 68% of the observations will be within one standard deviation. We knew that. But now, more importantly, reaching out. 95% of the observations will be within two standard deviations. So if I went out two standard deviations, both above and below, that's going to be 95% of my data observations. Okay. And then right after that, it says nearly all observations will be within 3%. Or sorry, three standard deviations. Nearly all observations will be within three standard deviations. And this nearly all, the reason why they say it's nearly all, there is a percentage here. It's actually 99.7, hence why we say nearly all, because you're talking about basically over 99% of your data. Okay, so they just call that nearly all. All right, here's a picture of the empirical rule according to, excuse me, the symmetric and unimodal distribution. So you can see some things here. They give you a little bit more accurate percentages, but I want to adjust these real quick. So this is a good picture. Do not get me wrong. It's great, but I want this to just be the 68%, and I should actually just leave the percent in there. I want this guy to just be the 95, and then of course you have the 99.7. Now up here, that changes some of these. So these little markings are now going to come. This is just 34 if we go with the 68. This guy right here ends up being a 0.5%, 13.5. This one right here ends up being, let me write these above. Change my mind. So 13.5, 13.5. This guy ends up being the, scratch that piece out, 2.35. And over here, this ends up being, it would let me draw, there we go, 2.35%. So that's a little bit better. So just wanted to kind of give you a breakdown. So this is, so if you fall between, and what these numbers are down here are the standard deviations away from the mean. Right here in the middle is the mean. Okay. So this is the mean. This is X bar, and this is how far you are away from the mean according to standard deviations. So if you are one standard deviation above, if you're between here, that's about 34% of the data. Okay, if you are between 0 and -1, or in other words, 1 standard deviation below, again, this is 34% of the data. And if I'm between 1 standard deviation on either side, above and below, this is 68, because 34 plus 34 is 68. Okay, so it's just kind of a breakdown of how much of your data is where on this. That's what these percentages represent. So between 1 standard deviation at 68% of the data. Or if I wanted to focus in on a certain column up here, if I'm between 0 and 1 standard deviation below, that's 34% of my data. In here, this is 13.5% of my data. In this little branch right here, this is 2.35% of my data. And over here, if I'm above or if I'm below, or in other words, if I'm more than 3 standard deviations below the mean, then that's 0.15% of my data. Okay, so that's all this is, just kind of a visual representation of what I put here in words. Okay, I like this visual representation. Definitely have this written down in your notes. It's going to become useful in some future sections. Okay, all right. So that's the empirical rule. And then right here is the z-score. Okay, what the z-score does is it measures in standard deviations how far above or below the mean an observation is. What's cool about this with the z-score, and as I noted it down below, it converts this into standard units. In other words, standard deviations. Okay, and the standard units, they're a measure. They measure a value relative to the sample. So they're talking about this number in terms of the sample rather than with respect to some absolute measure. So in other words, what it does when you find a z-score is you strip the units away. And this allows us to compare two different data sets. And if we find the z-scores for these two different data sets, it allows us to compare them side by side, even though these two data sets might be different. For example, many of you take my class on purpose because you like my style and things like that. And so after we take exam 1, we could go to some other class and see if, students that take that class, maybe they also say that their professor is a little bit harder. So we could compare the hard class to my styled class, even though we are two completely different styles of classes. If we find the z-scores for some of that data, we can compare apples to apples, because even though that class is harder and my class is, zany style and things like that, we're very much different data sets. The z-score allows us to compare from one to the other because it strips away all that information. Because the z-score compares it to the sample rather than in some sort of standard measure. So like a 65 in my class is at the same kind of 65 in another class. And a z-score allows us to compare that information. Okay, you'll see that come up here in an example soon enough. But that's what's cool about the z-score is it allows you to take away the label of like inches and percentages and miles or beats per minute. It takes that away and it compares it as a standard unit. Okay, so we can compare two different sets of observations, even though they might be completely different kinds of observations. Like I said, some people take my class because they think it's easier, and some people take another professor's class because they think it's harder. It allows us to compare these two kind of classes, an easy to a hard, even though we're definitely very different. Okay. So z-scores, just so you know, they strip away the units. It's in standard deviations. So kind of going back to this, these down here, the 0, the 1, the 2, the 3, those are z-scores. Okay. These are all z-scores down here because they're not in terms of what we're looking at. They're not in terms of feet, miles, and all that stuff. These are the unit measures that we just talked about, those standard units. Okay, so having a z-score of 0 means you're right on the mean. Having a z-score of 1 means that you are 1 standard deviation above the mean. Having a z-score of negative 1.5 means that you're 1.5 standard deviations below the mean because you're negative. Okay, so z-scores allow us to compare where we're at along this. How do we find z-scores? Simple. Here's the formula. Take your data value minus the mean, because that's what x bar is, and then divide it by the standard deviation. And that's your z-score. Your data value minus the mean divided by the standard deviation. So obviously from 3.1, we have to make sure that we know how to find the mean and the standard deviation. And again, you have your calculator and you have StatCrunch to help you out with that. Okay? Again, I like to use StatCrunch. So let's make sure that that's open for us real quick. So let's grab some StatCrunch. Let's minimize this information that's right over here in this corner. We'll get StatCrunch open. Because these are the two concepts that are in 3.2. All we're going to do now is take a look at problems that you'll see in your assignment and illustrate some of those ideas that we were just talking about. So StatCrunch. Get this open real quick. Because on some of these problems, you're going to have to find the mean and the standard deviation. Okay, sometimes they'll just give it to you, which would be great, but not all the time. StatCrunch is thinking about life real quick. There we go. Open StatCrunch. It should hopefully be opening. There it goes. All right. Almost in business. It's thinking. We're almost there. And now we're good to go. All right. Okay. So we got our StatCrunch. Let's start taking a look at examples. So right here, it says in 2011, the mean rate of violent crime per 100,000 people for 24 states west of the Mississippi River was 406. So that's the mean. So that's important. We know that. So X bar 406. Says the standard deviation was 177. So that means these states, they averaged 406 violent crimes, okay, per 100,000 people. The standard deviation means that this thing deviates by 177 above and below, okay? So again, these are all in that unit of violent crimes. Okay, these are not standard units like in the z-score. So keep that in mind. So it says assume the distribution of the crime rates is approximately unimodal and symmetric. Good, we like that. Okay, so it says what are the two values you would expect to find between 95% of the rates? All right. So what they want here is they want to know what are the two values, the top value and the bottom value for 95%, or in other words, the top value and the bottom value that are 2 standard deviations away. Because if you go back to that hump right here, 95% of my data happens right here to here. So that's 2 standard deviations above and 2 standard deviations below. That's what they're asking about. Okay? So, in order to find those answers, all I'm going to do, let me zoom in on this, is I'm going to, my page would not jump. I'm going to take 406 plus 2 times my standard deviation. Because I need to be 2 standard deviations above, which means I need to go up 177 and then up another 177. Okay, because every time you jump a standard deviation, that's 177 more crimes. Okay, so if you take 2 times that, that gives us the jump of 2. Okay, because again, kind of to illustrate this so you understand, right here is 406. If I jump right here, I'm going up 170 crime or 77 crimes. And then if I jump to 2 standard deviations, I'm going up another 177 crimes because this is what we call 2 standard deviations. And every standard deviation is 177. Okay? Your mean goes in the middle. And then as you keep moving out your standard deviations, you keep adding it in this direction, you'll subtract it in the other direction. That's what's really going on there. Okay? All right, so back to this. So this is just calculator work for you. Go to your fancy dancy calculator, take 406 plus 2 times 177. And the top value should be 760 violent 760 violent crimes per 100,000 people. Okay? The lower value, again, would be 406 minus 2 of the standard deviations. Okay? So that would be taking what I had just a second ago and then just changing the addition into subtraction, 52. So the top value, 760, the bottom value, 52. So between these two is 95% of our data. That's what they're asking about in part A. Go ahead, try part B real quick. Pause the video, give it a shot. Okay, so part B is a lot like what we just did in part A, except you're doing 68% of the data. 68% of the data is just 1 standard deviation away. So in part B, you're going to take 406 plus 177, which is just like what we did back in 3.1. And then we'll also take 406 minus 177. Okay, you could also take 406 plus 1 times this and 406 minus 1 times this, since you're going 1 standard deviation out. You basically, however many standard deviations you go out, that's the number you multiply by the standard deviation number they gave you in the problem. Okay, so if I take 406 plus 177, we get 583. And if I take 406 minus 177, I get 229. So this is the range for 68% of our data. Okay? That's all they want. That's using the empirical rule. So 68% of our data lies between 229 and 583. 95% of our data lies between 52 and 760. All right. So question C, work this one with you. So it says, if a Western state had a violent crime of 584 crimes per 100,000, okay, people, would you consider this unusual? And this one, so 584 happens just above the 68% range. So I would not really consider that unusual. It actually falls within the 95% range, but it's really close to being 1 standard deviation away. This is about 1 standard deviation away from the mean. So is that unusual? No. Generally, if you are about 1 standard deviation away from the mean, you're not unusual. Okay. Unusual. Okay. Reason being, because you're not that far from the mean. You're within 68% of the data. That's really, really good. Okay. That's where a majority of the data is at. Okay. So this is not unusual. Go ahead and part D, pause the video, give it a shot on your own, and think about it. Okay. In part D, if you looked at this, this is over 2 standard deviations. Because 2 standard deviations away at the bottom is 52. This is definitely under that 52. So anything that is usually over 2 standard deviations usually is what we would consider unusual. So we would definitely say this is unusual. Because again, if you think about this in terms of percentages, between here is 95% of my data. This 30 crimes per 100,000 people is out there in the other side. Think about this as the other piece of this. If you're over 2 standard deviations, that's only 5% of my data. Is that a lot? No. That's 5% of my data versus 95%. 5% it means that it's not likely to happen. Okay, so since this is over 2 standard deviations, the odds of 30 crimes per 100,000 people is very, very low. Okay, so I would definitely say this is unusual because that's over 2 standard deviations away. Now, again, remember in this, you're not writing your own explanations. It's all multiple choice. So you just got to make sure that you reason it out and find the one that's below that matches what you're thinking. Okay? See, not that bad, right? Go ahead and let's do A together, and then I'll let you do B and C on your own again. Again, this is a lot like what we were talking about a couple minutes ago. Okay. So let's think about this. So it says in 2011, the mean property crime rate per 100,000 people for 11 Western states was about 3,331. So we know, sorry about that, screen likes to jump. We know that X bar is 3,331. Okay. It says the standard deviation was 729. Assume the distribution crime rates is unimodal and symmetric. So here it says, what percentage of Western states would you expect to have property crime rates between 2,602 and 4,060? Well, when I take this kind of problem, what I do in this is I create a picture. I draw my own little symmetric diagram. And so right here at 0 is 3,331. A lot like what you saw me do a couple of minutes ago when I put the 406 on our little graph that was right here at the top. And I told you how we jump from one standard deviation to the next. I'm going to be doing that same idea in this picture. Okay? So scroll down again. So if I'm 1 standard deviation above, okay, that means I'm going to take 3,331 and I'm going to add 729. So 3,331 plus 729 gives me, not 40,000, 4,060. And that's one of the numbers we want. So I'm going to stop going on this side. So over here, I'm going to go 1 standard deviation below. So I'm going to take 3,331 minus 729. And that gives me the other number I'm looking for, 3,331 minus 729 equals 2,602. That's the other number I was looking for. So they want to know what is the percentage of your data that is between one standard deviation. And hopefully you realize that one standard deviation is 68% of the data. And that's what they're after. So they're reversing it. Okay? Instead of you finding the numbers, you're finding the percentage. Okay? So go ahead and try B and C and let us know, let me know what you think. Go ahead, pause the video, give it a shot. Okay. So to do this next part, so again, it's asking about a percentage. So we're going to keep adding or subtracting the standard deviation until we find these numbers. So if I go out to 2 standard deviations, all I really need to do is take this number right here and add on another standard deviation to it because I'm just jumping to the next one. So if I take 4,060 plus 729, that gives me 4,789. So that's the number we're looking for right there. And then if I go over here to -2 and I take the 2,602 and I subtract 729, that should give me the other number. And it does. 1,873. Again, all I did was take this number right here minus the 729 because I went another standard deviation. All I did was take this number that was right there and minus a 729 from it to get to this guy. So now if you look at this, those are the two numbers we're concerned with. So they want to know what is the percentage of my data between two standard deviations. And hopefully you said that this was 95%. Okay? Now, the last question says, if someone guessed the property crime rate in one Western state was 9,000, would you agree that that number is consistent with this data set? Okay, so in other words, is that usual for this? Does 9,000 happen? And hopefully you would say, no, this number does not agree with this data set because 9,000 would be way out here in our data. That's way above 2, okay, standard deviations away. In fact, it would be, I'm just figuring out a quick z-score, which we will do here in a second. In fact, that would be 7.78 standard deviations away. That's highly unusual. Okay? So, again, all I did was just figure out a z-score. I took 9,000 minus 3,331, because that's the mean, got an answer, and then divided it by 729, because that's the standard deviation. Because that's all you do to find the z-score. And again, the z-score tells you how many standard deviations that number is away from the mean. Pretty cool. So that's highly unusual. Anybody that has a standard deviation of any data value that has a standard deviation of 7.78, that's highly unusual. That's way, way out there, considering 95% of my data is in here. So no, I would not agree that that number is consistent. All right, last one. Like I said, this allows us to take and talk about IQs on a test. So the Wechsler IQ test have a mean of 100, a standard deviation of 15. Okay? So we've got a mean of 100 and we've got a standard deviation of 15. They want to know which is more unusual, an IQ of 115 or an IQ of 80. So in other words, you're going to look and see which one of these has the larger z-score. The larger the z-score, the more unusual it is. Okay? The larger the z-score, the more unusual it is. So I'm going to find the z-score for this first one, 115. So I usually just put z and then the data value that I'm working with. So I'm working with a data value of 115. So all we're going to do is take 115 minus 100, and then we're going to divide that by 15. Okay? So if you take 115 minus 100, that gives you, 15 divided by 15. So this z-score is one standard deviation above the mean. Okay? You figure out the other one. Figure out the z-score for 80 and go. Okay, so hopefully you took 80 minus 100 divided by 15. And in this, they will want the decimal. And they will usually have you round the decimal to the nearest hundredth. Okay? They will want you to round the decimal to the nearest hundredth or two decimal places more often than not. You'll understand why later on. So if you round this to the nearest hundredth, you get negative 1.33. So which one is more unusual? Hopefully you said the IQ of 80 because it has a larger standard deviation. It is further out. This is more usual, okay, than unusual. And again, you could do this between two different IQ tests. We could talk about this test and then another IQ test, which has a different mean and standard deviation, and we can compare IQ scores and see which test was more unusual, even though they might have been two different tests. It's really, really cool that because z-scores strip all that information away and compare it in terms of the data of what's really going on. It's really cool how z-scores can do that to allow you to compare two things that are really kind of different in nature. I mean, they're both IQ tests, yes, but some of a lot of IQ tests have different measurings. Just like when you apply to go to college, some of you took an SAT, some of you took an ACT. They're completely graded differently. But you can talk about their mean and standard deviations and see if your score is usual or unusual for a standard in terms of the SAT and the ACT and things like that. So some really cool things can happen. So yeah, there we go. And so your questions for this section really come from questions 14 through 23, and they're all over the empirical rule, and they are about z-scores. So remember, all this works for symmetric unimodal distributions. Okay? All right. Until next time, my friends, I will see you then.